We get started? All right, welcome back, everybody. Let's get started with the last lecture on quantum simulations with ultracold atoms. So today is going to be more slide focused, more showing you some of the experiments. But keep staying as interactive as you have been. So please do interrupt me if some things are not clear and you want to know more. So let me first start with quantum gas microscopy. I mean, we didn't talk so much how we actually detect the atoms, how we can manipulate them. And one technique about 10 years now I developed is this idea of using fluorescence imaging to image those atoms that we trapped in the lattices that I explained to you before by just making them fluoresce. So imagine you have the following setup. You have this lattice. You maybe have occupied one of the planes of the lattice. You can have additional lattice structures in the XY direction. And then you turn on a near resonant laser beam that scatters light off those atoms. And this light you can then collect with a good microscope and just image it onto a camera. So just standard fluorescence imaging. And that works actually quite well. Here's actually a nice image of one of my former postdocs, Jaeon Choi in Korea now, showing you this for lithium-6 atoms, bosonic lithium, a large array where you can really very nicely see each individual atom on this lattice. Each spot here is an atom on that lattice side, and you can really see that the fluorescence that you get from those atoms is really quite large. So the signal-to-noise ratio that you get with the atoms is really exquisitely good. You need to, of course, image a bit longer than, for example, with tweezers. If you compare that with tweezers, the distances here, remember, they're about half a micron, 500 nanometers. And you see the point spread function of the imaging system, which basically determines how big the blob is, right? That's just determined by the imaging system, resolution of the imaging system. In order to really discriminate atoms when they get so close, you need more photons. You just need a better signal-to-noise ratio to separate, tell apart where an atom is. Whereas if you have, let's say, okay, think about it for a tweezer, you would have one tweezer here and the next atom here. Of course, you need much less photons to tell whether there's a photon on that side or that side. So it comes at a price that we want to do this itinerant physics, that the atoms should hop through the lattices, that we have to do a bit more on the detection side. But by now, there are actually very many of these. I just give you the periodic table of, I don't know, quantum gas microscopes of the world. There many more by now also in all over the world where people are doing this with very different species of atoms, bosons, fermions, magnetic atoms. Yeah, so I think the main challenge is really you want to combine. You see, I didn't talk about it so much, but let's very briefly think about it together. I mean, imagine we have this physics lattice. Let's call this the physics lattice, and there we do what the physics we want to do. Okay, Hubbard physics, Rydberg physics, whatever. And then we want to detect the atoms. And when we want to detect them, I told you we're going to scatter light off them. So we're going to shine light in here. And we're going to scatter light here, and we're just going to collect this light with a lens. Now, when you scatter light, you inevitably heat the atom. They're going to be heated by the photon recoil. They're being kicked, and each time it's basically approximately recoil energy, which is just h bar squared k squared divided by 2m, where k is the wave vector of your light that you're shining onto the atoms, and m would be the mass of the atoms. So that's just how much you heat up per photon scattered. But here we want to scatter a lot of photons. We don't want to just scatter 10 or 20 photons like for tweezers. We want to scatter ideally about 1,000 photons or more that we collect then, actually even on the CCD camera, taking into account the solid angle. So they're inevitably going to boil up. They're going to heat up here. And that's going to be a problem because once they're in these higher bands, remember I told you also in the higher bands, the tunnel coupling is much larger than in the lower bands, 100 to 1,000 times larger. So now we might hop to that position. And that's, of course, totally because then you have a detection. You would see the atom that originated from here suddenly appearing here in your detection process, and you don't want that, of course. So you want to have a faithful image of the atoms in your physics lattice. The trick to do that is to crank up the lattices, make them freeze during detection, freeze any motion, so make the lattices extremely deep. And while you're shining this light off them to make them fluoresce, you're simultaneously laser cooling them. So you're trying to not have them climb up that ladder too much. So you're fluorescing, at the same time you're cooling, and we characterize this. So for example, how do we characterize this? We take a first image of the atoms, and then we take a second image. And then we look for the difference between the two. And then we can see what we call our hopping events, okay, where maybe there was a thermal, it could actually be also a thermal activated over the barrier hopping, right? Because something that goes over here is also possible. And we just look for that and we try to minimize that, of course. So that's how we check that we really make a faithful image. And again, what is more difficult for us, and with the tweezers, we really want very deep lattices, very powerful lasers to have also large system sizes. And I think just getting everything together, you know, made it difficult. To combine that with the lattice setup itself, the complex geometries made it challenging. All right, very good. Yeah, so you can detect the images. You can see, for example, measure, for example, nicely, you know, when you go to this mod insulating state that we talked about, you can see how the atoms order one by one. In this lattices, we get the Fock states, whereas in the BC state, you have this Poissonian distribution, which just gives large number fluctuations. We talked about that. And then you have the ability also, of course, to engineer potentials. So, you know, we have the lattice, but then we want to confine the atoms in some potential. And by now, there are actually very nice techniques to do a lot of different kind of potentials. You could, for example, just have a box potential, really make the system homogeneous. So you don't have a trap or something, harmonic trap, you can make it completely flat. And there's the lattice inside and there are hard walls here. You could make exotic lattices, or you could, this is also interesting, this has been done a lot by Tilman Esslinger in Zurich. You could study quantum transport. Think about two boxes connected by a very thin wire of light, okay? You fill up the atoms in this box is empty, for example, then you study how they flow through this maybe single mode channel or multi-mode channel of light from one box to the next, and then you can have interactions, magnetic fields, gauge fields, I know, disorder, whatnot. So what you ever want to look at, and then you can measure. That hasn't been done yet, but I'll show you some experiments towards that, where you could really measure one by one the atoms arriving there. That's of course cool, right? Because then you have access, and we'll talk about that, to the full counting statistics of the transport process. There's also single atom addressing. We can do single atom addressing. Of course, again, we're hit by the same challenge that I outlined before. Our spacing is 10 times smaller than for tweezers, so it's harder for us to do that with very high fidelity. But it's possible. We can go in and flip, let's say, individual spins, but not with the super exquisite fidelity that the ion trap people would tell you typically, or the Rydberg tweezer trap people would tell you. But it is possible, and to study, for example, flip spin impurities propagating and things like that. So here are the systems that we can do now. We're up to about a few thousand atoms that we can have, and in this mod insulating state, here in the case of bosons, with fillings as high as 98%. So this 98% means with 98% probability, there's exactly one atom on that lattice side, on each lattice side. Okay. And this is one where they're actually very close together, and you can't resolve the individual atoms anymore. But you can see when there's one missing, there's this black dot in here, or like in this experiment here. But using, you know, our imaging algorithms and making use of the fact that, you know, these atoms are not randomly positioned, they're on a lattice, we can still reconstruct where the atoms actually are on that lattice, even though our resolution is a little bit less than, you know, seeing them light up as individual spots here. If we increase the spacing a bit, you can see then, of course, we can see them light up individually again. We can terminate the system, you know, under different termination conditions. This is interesting. I'm not going to talk about it a lot, but for example, if you have ladder systems, having the right edge termination can determine whether the system is in a topological phase or a non-topological phase, for example. So this is done, for example, with fermions on such a ladder. If you terminate like this, you get a SPT Haldane spin 1 phase. If you terminate straight, you get a topologically trivial phase, and you get edge states and string order parameters that you can measure in these systems, but don't want to talk about it in this lecture, but you can ask me about it if you're interested in that. All right, now how can we improve on the detection? So far, I just showed you, well, we just see there's an atom or there's no atom. In fact, it's actually even worse. Most of the image you see in these quantum gas microscopes are so-called parity projected images, just to give you an idea of what happens. So the problem is that if you have two atoms on a lattice side, in most of the experiments you see, what happens when you turn on this near resonant light for fluorescence, there's actually an inelastic collision process. and these atoms get actually lost. So it's like a small bomb going off, but it only happens for pairs of atoms. So if there's one atom here, it's fine. If there are 3 atoms here, that 2 of them are going to be killed, 1 is going to stay. So that's why we call it parity projected detection, because what you're actually measuring is not the actual density, operator, but the parity of the density operator, right? Okay, so that's of course not, yes?
I remember in Twitter, this process limits the splitting fraction.
Yes.
So why in lattice the splitting fraction?
Because, very good, because we don't use laser cooling to fill the lattices. Because we use evaporative cooling. You're completely right. In tweezers, this would limit you to having either 0 or 1 atom. And if there are 2, they get lost. They try to be in this blockade regime to make use of that, actually, to kill that. And then you get with 50% probability 1 atom and 50% 0 atoms. Here we do it differently. We don't use the laser cooling to cool the atoms into the lattice. Remember, we do evaporative cooling, and then we basically make our Bose-Einstein condensate or degenerate Fermi gas, then we adiabatically ramp up the lattice. So it's a completely different way of preparation. Okay. So we don't have to do any active sorting. These are not actively sorted arrays. Okay. These are just the atoms doing themselves through the strong repulsive interactions, sorting themselves into a single occupancy per lattice site on whatever geometry of the lattice we place. Okay. Whereas for the tweezers, you have to move them. And in the tweezers, of course, you also cannot be sure. I'll come in the end how we could combine both techniques. In the tweezers, you can't be sure they're in a motional ground state. That's very hard. In the radial direction, it's easier, but in the longitudinal direction, it's not so easy. Here, they are in the absolute motional ground state also, in all 3 directions. Okay, so that's important. Very good. So this is the parity projected imaging. Obviously, that's not so nice, especially if you think about fermions. You don't want that, because for fermions, if you want to do strongly correlated electron physics, you're dealing with the following situation where you have, your spin up and spin down atoms. There can be holes, which can be quantum fluctuations or dopants, and there can be doublons in the system. And really, you want to detect all of that. Because really, if you think about the problem, talk about it, the problem here is really how do mobile dopants interact with this antiferromagnetic background is what you actually want to learn about in this system. So we have to do better, and we can, and we do it in the following way. So if this is the physics lattice, this is the physics lattice, and with the occupation we would have, for example, we want to image that. We do the following trick. We actually split each plane into 2 planes, and the way we do that is so-called via, get some white chalk, via optical superlattices. So you basically take a single lattice site, and via a factor of 2 shorter wavelength, another lattice that is aligned with that, you can split each well of the original lattice into a double well of the superlattice. Okay, but just having another standing wave which has a factor of 2 shorter wavelength. So you go from here to here. And then you do this under the action of a magnetic field gradient. You keep a B prime also on during that splitting process. And let's imagine you would have spin up and down here with opposite magnetic moments. What's actually now going to happen, they're just going to separate to the left and to the right. So it's like a Stern-Gerlach separation, but in a highly controlled way. Really in between one mode going to these 2 modes here. So this atom will go here, and this atom will go here. And now you've avoided the double occupancy. And now you have to just image this plane and then image that plane. Okay, think of these in the Z direction where these would be, single sites. And we're doing this splitting process actually in the vertical direction, the superlattice, what I'm talking about. Now here, the spacing is still too close to image them. We wouldn't be able to resolve them. So we have to first separate them over larger distances. And what we do to achieve that is actually invoke a Thouless pump. So we actually do some interesting topological physics where we can separate the planes over large distances while keeping the occupation of the split process. So we split and then pump and then image. Okay. And then we first image, let's say, tune the microscope objective to image the upper plane. Then we tune the microscope objective to image the lower plane. And then these are in focus. First, these atoms are in focus, then these atoms are in focus. And then we just have the images of the spin ups and spin downs. And then we just have to combine them to get the image of the total density. Okay, that's how this works. Yes.
Sorry, no, there was.
Yes.
So does that mean you can also produce 3D lattices?
Yeah, sure. We work with 3D lattices, but for this experiment, mostly what I'm going to talk is 1D and 2D, because the imaging works best here because we need to, this the third direction to do the splitting. And anyway, the physics in 1D and 2D is a bit more interesting than 3D, but it also means what we can also do in such geometries, you can do bilayer physics. Bilayer physics is interesting again. So, yeah. Very good. Correct. Well, Moret not that easy. When that doesn't work like that easy because these lattices are not rotated against each other, right? There you could do something like Moret lattices where you have spin-dependent lattices where one spin state sees just one color of your laser beam, and which is one lattice. The other spin state sees another lattice, and they're slightly rotated to each other. And then you can couple those two states, so you can have tunable couplings between the bilayers. So that's all people have thought about it, but haven't realized it yet. Well, we did bilayers, but not Moret bilayers or something. Yeah, but a good idea, yeah, definitely, absolutely. Okay, and this works then quite nicely. Just some older images showing you that this works. So you get you have the physical system, you do the Stern-Gerlach, you pump, you image, you reconstruct where the atoms are, and then you just put the two together, and then you know what the original occupation on the lattice was. But now you have the full spin and density resolved image, right? You know where the spin up is, where the spin down is, where the doublon is, where the hole is. So you know everything, whole occupation of the system. It's a full reconstruction. Of course, if you think about it, the state, in general, will be a superposition of different configurations. And when you do this strong measurement, your wave function is just going to collapse on one of those configurations, right? So what you actually see in one experiment is maybe this outcome. And after that outcome, the system is dead, right? You collapsed it onto that state. So it's not in psi anymore. So you actually have to go through the whole cooling cycle again, create psi again, and then do another measurement. And we do that, sometimes we have to take tens of thousands of shots. And that's where, of course, then cycle times start to matter for these things, are very relevant, of course, to get a lot of the statistics in this, because in the end of the day, what you're going to get in the experiment is the probability of this configuration, the probability of that configuration, the probability of that configuration. So what you get as an output of the data is probability of configurations of these snapshots. And from this probability of configurations, you can go on and then calculate correlation functions, also higher order non-local correlation functions. Now I've swept under the rug the C coefficients here a bit, right? Because there are, of course, phases also here. What we just measure is the norm squared, the probabilities of these configurations, of these coefficients. So measuring the phases is actually hard. If you want to do that, you have to do some many-body interferometer setting. That's actually quite difficult. But some of these phases show up in different quantities like the current operator. So here we're measuring the density operator, but you can also measure the current operator. If you're interested, for example, in measuring, not the occupation on a lattice, your lattice here. And what we do now is just really measure local occupation. So we're measuring a measurement of Ni. If you want to actually measure the current operator, Jij, that's actually also possible. We know how to do that. And just to give you a hint how that works, again, you use these super lattices to isolate. You have your physical system and you want to measure the current along this bond. The way to do that is just to isolate that bond into a double well system and then do just a Josephson oscillation, half a Josephson oscillation. That converts then, if you measure the left-right occupation of that system after the Josephson oscillation, actually constitutes a measurement of the current operator. So that's how you can measure current operators, and of course also current operator statistics and current correlations. We can correlate this current with the current on this bond, for example. And that's of course very interesting if you think of especially the artificial gauge field systems, where of course you're going to set up some currents in these systems. Okay. All right. Yes.
The output of this experiment was the probabilities, but you actually take enough shots to get access to the full probability distribution of all these states, or?
Good question. Yeah, I mean, of course, if there are too many outcomes or they are very low probability, we can't. But they typically for physics problems, they won't be very relevant either. So that's the benign thing of quantum simulation that makes it much more benign than a quantum computation. Also, if you make one error on your quantum computer and you don't correct it, it's fully wrong, the calculation. Here, it doesn't matter so much, or you miss a very low probability configuration, probably doesn't matter so much either. Yeah, but you're completely right. Yes, that can be, of course.
Yeah. Monte Carlo sample.
Yeah, and that's of course a good question. It actually, I think it's not worked out in all cases. What's the sampling complexity for different observables, for different non-local observables? How many data shots do we actually have to take to tell you, I want to measure this 8-point correlator with 1% precision, even if everything else is perfect? So it's a very interesting question, actually. All right. Good. So yeah, let's talk just briefly about the Fermi-Hubbard model, since we now have set up everything to do that. All right, yeah, I guess you're all following this exciting news on high temperature superconductors on Twitter, as I'm doing. No news so far this morning, at least. Anyway, so this is the standard, more copper oxide-based scenario, where for undoped systems, 2D systems, you basically have an antiferromagnetic setting, and then you dope it, and you get this very interesting phases here. And I think by now we understand that the Hubbard model does play an important role in describing these. You need some frustration also in these systems to really get superconductivity, but already on the square lattice turns out to be very interesting, and still many open questions. Numerics is getting better, but I still think there's a strong motivation to do that, as I'll show you in a second. So we're going to start out at half filling with strong repulsive interactions, where we talked about you get the antiferromagnetic Heisenberg model because of super exchange in the system, and if we're cold enough, you basically get this antiferromagnetically ordered state. And what you really want to understand in this problem is really, if you dope it, this antiferromagnet, how do these impurities interact with the magnetic order, with this antiferromagnetic order? It turns out actually to be a tricky question that has captured, theorists for decades now, actually working on this problem. Just want to show you that we really can make quite nice where we are in terms of temperature on these systems. So this is just the way how we do it. So we make this shape the potential with the confining potential at the top of the lattice into different regions. There's the physics region here connected to a reservoir region, which acts as a cooling reservoir in the system. And then we can measure quantities like the density or the number fluctuations, for example, on each lattice site. And you can see that we nicely make this n=1 core, the mod plateau. You can see it has a little bit of quantum fluctuation still, because it's finite U/T. So there's supposed to be some fluctuations here. And we can measure the spin-spin correlations. And if we look at the spin-spin correlations, you can see that they almost extend over the entire system size. So the antiferromagnetic order. And we can compare to quantum Monte Carlo. These are some quantum Monte Carlo calculations from Lode Paulet. This is the data. And you can see that this one compares quite favorable with the 1/4 T temperature. I think the lowest we've reached by now is 0.2. And so that's the temperature range we're working in. This is actually very interesting. 0.2 is getting me excited, but I don't know, you probably doesn't mean a lot to you whether 0.2, what is it, why is that interesting? Turns out around 0.16, theory expects a lot of interesting things to happen. So right now, T/T, so temperature in units of the hopping at U/T around 8 is 0.2 to 0.25. If we get down to a 0.16, then a theory predicts at least a lot of interesting things to happen. Then for the doped repulsive side, we should see stripe phases. On the attractive side, we have FFLO phases, so an unconventional superconductivity happening. And so we're not very far away from that. So that's why we're excited about it. We have to push a little bit lower in temperature, but then things start to get very interesting. And already to do QMC for these doped systems gets very hard. Then when I talk to Lode about this, a few percent doping they can do, but more doping they just can't do anymore in QMC. So already at these temperatures, so then they can only go to 0.4 T/T in the QMC simulation. So this gets very competitive with what you can do in the best numerics. Okay. Again, I don't want to talk about quantum advantage or supremacy, but it's definitely pushing the boundaries of what theory can do. And that's, of course, very exciting. And it's also exciting because you can use these data, of course, then to compare, to check your numerical methods. If you're a theorist and you want to check your numerical method, I think this can provide really high quality data for you because the model is so controlled. Yes. Yes. Well, in this picture, you can see it's connected to a reservoir. So there are number fluctuations also in the system. So it's more like grand canonical system. But it's not connected to anything else. So very good question. So we have to better think in terms of entropy when we do adiabatic changes to the system. You conserve the entropy. We start out with a certain entropy. And whatever adiabatic change we do, we cannot get lower than that total entropy per particle, right? But we can, what's nice is, and this is what this picture also shows, we can push the entropy to different regions in the system. So that's what this effort tries to do. It tries to create metallic regions in the outer side where we can trap a lot more entropy than in a mod insulating core. So entropy in this case, the total entropy is the same, but it's just pushed out to the boundaries, and the core is rather low entropy core, and is of course where we want to do the low temperature physics. So that's the trick of trying to cool this down to low temperatures. But you're right, we should better think about entropy, but that of course converts to some temperature for the system that we compare to, that we can then compare to theory. Okay. All right. More questions? All right. Okay, I want to show an application to you just, for we're talking more about dynamics in the 1D Fermi Hubbard model. So and it is about spin charge fractionalization. And I think I like it because it's, first of all, makes you understand what this process is about, and also shows you what new quantities you can really measure if you access these non-local correlators. So, so electron, our electron, has a big one, yeah. It says two quantum numbers as charge and spin, right? And of course, we can't separate the two from each other. The interesting thing is, if you do that in a solid, you can do that. You can take an electron, inject it into a solid state system, and it can fractionalize into two quasi-particles, one which carries the charge and one which carries the spin. And if they would be deconfined, that means they can separate over arbitrary distances. So now you've done something that seems hard in the outside world, but in a solid state system, you can do that. And a very simple way how you can see that is that you can do that in a Heisenberg, 1D Heisenberg antiferromagnetic chain. Here's just my proof that we have a 1D Heisenberg chain showing you the spin-spin correlations. And then we can do the following experiment. We can take this Heisenberg spin chain, take a laser beam, focus it on one side, and just shoot out one particle. Okay, we could inject one electron, but we can also just remove one. That's actually going to turn out to be essentially the same physics that's happening in the system. So we just remove one from the system, and then what happens in this cartoon, you can already see what happens. Okay, this hole is going to start to move by these atoms hopping in from the side. It looks like the hole is moving. But then there's another particle that's left over here, and this is the spinon. Okay, so this is this particle that carries the spin 1/2 quantum number, and this is the charge particle here, the holon, which carries the charge quantum number. And indeed, if you go through the math or just look at it, you see that the energy configuration does not depend on the distance between the two, which means that they are deconfined. They can separate over arbitrary distances. Which is actually very different in 2D, but I don't want to talk about the 2D connection. There you cannot separate over arbitrary distances. Actually, just one question, since you might be wondering, why is this a spin 1/2 object? I mean, it doesn't look like a spin 1/2, right? If we would have looked at it immediately, I would have thought, well, it looks more like 1 or something, right? Why is that spin 1/2? Let me show you, okay, the experimentalist way of understanding why it's spin 1/2. Let's take the Heisenberg chain again. Oops, this one. And let's rotate, not flip to shoot out that spin, but let's just rotate it. Let's turn it from spin down to spin up. Now we've changed the spin. How much? We've changed delta S by 1, because we went from -1/2 to +1/2. Right? Now, if you do the same, look what happens here. Actually, you will see you get two objects propagating out. One is this 2 spins to the left, and the other one, the 2 spins to the right, and align with each other. You do the same kind of cartoon, what I did before, and you find you get something like this after a long evolution time, 2 of these spinons. Okay? Well, if the total spin is 1, and you get 2 of them, then the spin of each of them is 1/2. Okay, that's okay, my naive experimental way of seeing that this is a spin 1/2 object. that you have here that carries actually that. Now, how can we measure that? And maybe you can already start thinking about how can you measure that in a real space picture. So you have something like that. I mean, you don't know if it's really actually 2 spin ups. It could also be 2 spin downs because you don't know, where you were kicking out the spin, whether these 2 spins were pointing down or up. It's, it can be quantum fluctuations, could be any direction. How can you actually see that? All right, and they propagate with different velocities. Yeah, we can measure the velocities, so we can see how the hole propagates. It just does a quantum walk. That's like a single particle quantum walk. We can measure the probability distribution of the hole. And we can also look at next neighbor spin correlation gate. And you can also see that the spinon apparently is also spreading out. And we can, from the cones here that you have in both cases, we can see how fast they spread, and we can determine their propagation velocities. And you can see that the holon here spreads much faster than the spinon in the system, which are just the different propagation velocities of the 2 quasi-particle branches that you have for the spinon and the holon, right? Yes. No, you just, no, you just do that, and then now you just, by a super exchange, you flip the spins in. You just if you just do super exchange evolution, you flip the spins in here, you flip the spins in here. Just for this flip-flop spin exchange motion, you will find that you actually get 2 of these spin 1/2, 2 of these blocks that go out, that separate from each other. You don't believe me? Then let's do it together in the pause. I'll show you that it gives that. Okay. Now, okay, that's just measuring 2 spin velocities. I want to show you actually one very nice way of measuring spin charge fractionalization. Is not looking at 2-point correlators, but looking at 3-point correlators. So the correlator I'm showing you here is a spin-hole spin correlator. So it measures how are the spins to the left and to the right around a hole aligned. We need 3-point correlator. We need to know where's the hole, and we want to know how the spins correlated around the hole. Now at time t equals 0, when you shoot out the hole here, you actually know that in an antiferromagnet, the spins will be aligned ferromagnetically around the hole. Right? You don't know, they could be both spin up or both spin down, but they will be ferromagnetically aligned around the hole, which means that this 3-point correlator is going to be larger than 0. But when the spinon has separated from the holon, when this thing has really moved into different directions, you actually see that the spin-hole spin correlator has become negative because the spinon has been liberated from the hole. And this directly shows you, is a very nice way of seeing the spin charge fractionalization by seeing how the spin-hole spin correlator actually turns from positive to negative. And we can see that in the experiment. It starts out positive and then turns out negative and then settles on some background negative value in the system, showing you that indeed as the spinon, which was originally around the holon, has moved away and is not attached to the holon anymore. Actually, you can also think about cool experiment where if you're in a trap, you could make the spinon come back and reattach to the holon again to form the original electron again, but in a continuous system, they would just continue to separate. I want to show you another way, I told you a bit more, how can we see the spinon? And I like this idea because it goes back to a very old idea from Steve Kivelson and Bob Schrieffer, how to detect fractional charge in SSH chains. And what we can look for, remember, when what we're trying to do, we're somehow trying to capture this additional magnetization of the spinon. We don't know whether it's up or down, but what is that going to do? Well, if I look at a finite subsystem of my system, then this spinon pointing up or down will have introduced additional magnetization fluctuations in the system. So it's something you can't see in the expectation value of the magnetization. So, because if I calculate the expectation value of magnetization here, indeed, we would have an excess spin half. But if it could also point down, that would average out to 0. But if you look at the S² operator, the magnetization squared operator in that subregion, that will lead to enhanced fluctuations in that subregion. How large compared to the background? Well, exactly your spin 1/2 quantum number, exactly 1/4. The fluctuations have increased by exactly 1/4 of the magnetization in the system. And this you can actually measure. So you can define a non-local operator which just measures the sum of the spins with some windowing function in your system over some area, and square that gives you the magnetization fluctuations, and then you can compare them to the background magnetization fluctuations. And if you've made your windowing function large enough to capture the whole wave packet of the spinon, this will give you 1/4, because the spin is just 1/2, so the fluctuation will be 1/4. But your windowing function has to be large enough to capture the whole wave spinon. If it's smaller, then of course you're just capturing a fraction of that. But that allows you also to check how large is the spinon wave function. You just change the windowing function in the analysis, and you see once it has hit 1/4, that's the size of my spinon wave packet in the system. And this is how this looks like in the experiment. So this is some experimental data. You're dealing with a Heisenberg antiferromagnet, so you also have a lot of background fluctuations of magnetization. So it's not this nice Néel 1-0 up down pattern, but you have a lot of background fluctuations. This is your offset. And then once you remove the spin, you can nicely see how you get this excess fluctuation, magnetization fluctuation. And if I would show you the data for longer propagation times, this would just propagate out in the two directions. So this is the way how you can track a spinon by looking at non-local correlators. This is a non-local correlator, right? Because it involves the sum over SZs over many sites squared. So it's something that has a non-local correlation value that we need to evaluate. And only when we have access to these snapshots can we measure that. Okay. Good question. In principle, now you come to my question, how many spinons do we create? In the t = 0 case, we exactly create one spinon. Deterministically. If we would be at absolute 0 temperature, each time we shoot out a particle, exactly one spinon is created in the system. Now, we are not exactly at temperature 0. And in these older experiments, we were around 1 or something, 0.5 of J of exchange coupling. And so that means actually, because there could be thermal spinons around, that just from the thermal activation could be some spinons around. That means that actually, when we shoot out a particle, we might not have created one because there was one there already. Okay, so we're creating them with less probability. And in our case, we create them at our temperature with around 50 or 60% probability. And if you would go really to 0 temperature, it would be a completely deterministic process. So this explains, if you're at finite temperature, how the spin charge fractionalization is modified in that case. And then, of course, you don't expect to measure the fluctuations to go to 1/4 because the background already has thermal background spinons in there. So it would be a little bit less. And this is what we used to explain. Sorry? The blue data is for holes. They fish the probability to kick out a hole. So in terms of mod insulator, we have nice. There's nothing, no defects in the mod insulator. So really, we always remove one atom. But here you can see there could be spinons around. There could be spin excitation. Spinon excitations already around at the location where you remove the particle, and then you can't create another one that's already there. Okay. Okay, very good. Let's move on. A little more complex things, but I thought it's still nice. I still like it because it's such a nice example and connects to really, I think, in fundamental physics. But I think it also takes away some of the mysticism of this spin charge fractionalization. When you think about it in real space pictures, what it actually means, I think it helped me a lot to understand actually what's going on in this process. All right, the next thing I want to talk about is thermalization in many body systems. And I want to show you a nice experiment from Markus Greiner's group that he did on that. And you all know, of course, that in the ETH idea, if we start out with a pure quantum state, we just have unitary dynamics. The whole state, of course, has to stay pure. But if we look at subsystems of that global system, and these subsystems are small, then basically these look like thermal states. And so we can then describe the density matrix in the subsystem by a thermal density matrix, where the temperature would be just given by the energy density in my system. So really what we want to know here is what is the von Neumann entropy, for example, of this subsystem, of this reduced density matrix. And that actually is the thermal entropy that corresponds to the thermal entropy in the system. So to show that a system thermalizes, we're going to actually see that's actually harder than showing that a system is MBL. Or we'll come to that in the end. That will maybe my final comment at the end of the talk. When you want to show that something thermalizes, you want to show a couple of things, right? You want to show that the global state remains pure. You're not coupling somehow to the environment because we want to have an isolated quantum system. So we want to show that that's pure. We want to show that locally the system looks thermal. And ideally, we maybe also want to probe this von Neumann entropy to show that it corresponds to the thermal entropy that we would expect from our different canonical distributions in the system. Yeah, question? No? All right. So how do we measure, how can we measure the purity of the system? And there's actually a very nice way how to do that. And von Neumann entropy or Renyi 2 entropy actually is, that's been basically a generalization of Hambry-Brown twist interferometry. So you basically, the idea is, and I'm not going to explain it in detail, but you can look it up in those references, that you take two identical copies, you prepare two identical copies, you, for example, induce some quench dynamics in both of them. And since they started out ideally identically, and if all of the Hamiltonian dynamics is the same, then you're going to have the same system here after some time evolution, T evolution. And then you just do a beam splitter operation between the two copies, just a swap operation, and measure the parity of each of those now outcomes of those beam splitters. Take the product of that parity measurement, and what you can actually show then, that gives you a measurement of the purity of the system, or the Renyi 2 entropy, which is just a logarithm of this Renyi 2, of this purity of the system, right? Plus different smaller subsystems also. And this actually has been shown that this is a bound to the von Neumann entropy. So when you measure the Renyi 2 entropy, von Neumann entropy always has to be larger than the Renyi 2 entropy. Okay, so here's the experiment from Marcus. What he did, he started out with 2 mod insulators. I mean, this is small systems, but a couple of years ago, but the idea is very nice and works very well. So you start with your 6 atoms in a row. You prepare identically 6 atoms down here in your mod insulating state. Then the quench dynamics he introduced was just to quench them into a superfluid state. So then you will have a lot of dynamics. So you suddenly change the lattice step, change U over T, strong dynamics happening in both of the cases. Then you do the beam splitter operation on each of the bonds. You measure the number of particles now on the left and right side after the beam splitter. And the way they do that without having to worry about parity projection is that if this is your original physical system, they just let all the atoms expand into 1/2 of the space. So they just let them tunnel into one side. So these 2 atoms here, they were originally 2 atoms on that side, but now you don't have parity projection problem also. So you had, if I want to reconstruct, that would be 0 atom, 0 atom, 1 atom, 2 atoms, 2 atoms, 0 atoms, 1 atom, 0 atoms. And then the parity of this detection gives me -1 or 1. I multiply those numbers, and that will give me the basically the purity of my state, of my global state that I have in the system. And here's the measurement. So you start out with this mod insulator, you evolve, you do this many body interferometer, you measure the state purity, and it's really very nice to see that over up to about 100 tunneling times, the system stays really very nicely in this pure state. You can really prove experimentally that you're not coupling strongly to the outside world. So what you are seeing is really the intrinsic evolution of the system. And that's the #1 check we had to do to show that it's thermalizes, right? We want to show it's an isolated system. So purity of the total system remains high, does not drop. Yes. Well, of the original, yes, but while you're including that parity measurement would include any state imperfections. If you don't have identical states to start with, that would also lower your purity value that you have here. So yes. So then you would start out with a lower value maybe, but still if the system would couple to the environment, you would see that dropping down. Okay, so take that. So about 100 coupling times, that's very nice. The system is really isolated. Okay, that's very nice that you can show that experimentally, and I don't have to believe me. All right, was another question or? Yes.
Just to bad at reading long scale plots, what sort of values are those at the top of that right plot?
This one, I think this must be probably 0.7 or 0.8, I think. I don't know. Yeah, I think it's probably on that scale, 0.8. But we can look it up. In the paper, it's really printed in numbers. All right. Now, if you look at the on-site statistics, you see actually a lot is happening. If you look at the local number statistics, you're starting out with an n=1 state, so you just have one atom per site. But then after you evolved in this quench, you see you nicely get to this Poissonian distribution, which is actually very much what you expect for the superfluid of a Bose-Einstein condensate, of course. Remember, that should be like coherent states. The superfluid states, coherent states have Poissonian statistics. That's what you're seeing basically here. Okay. But you can do more. You can now partition your system in different subsystems. The subsystem can be size 1 subsystem, size 2, size 3. And then for those subsystems, you can calculate also the Renyi entropy. You just have it in your data right away. And you can actually nicely see how, as the subsystem gets larger and larger and larger, how the Renyi entropy grows. And we're really generating a thermal state with this Renyi entropy growing and then saturating here to some finite value. If we look at the entire system again, there should be nothing because the entire system just stays pure again. The Renyi entropy has to stay exactly the same, right? And now we can also go and compare, to these different canonical ensembles. So what we get, so we have, different statistical ensembles, microcanonical, canonical ensembles, for example, grand canonical, and we can look at, for example, the probability distribution of different subsystems. 1 side, 3 sides, and look how that compares with the different statistical ensembles. And you see they're more or less all the same, but they very nicely capture what you measure in the experiment. So the experiment looks locally, as we promised, like a thermal ensemble in all the quantities we measure, but globally it's still in a pure state. Okay, and that's a very nice way of showing this thermalization. We'll do this a little bit. We'll come back with slightly larger systems, but the general concept, of course, also works for larger systems. All right, very nice. So let's go a bit more in this quantum dynamics and some newer things. So all this quantum dynamic stuff is, of course, very good. I guess you've learned by now. If you want to achieve a quantum advantage, ultimately, any experiment will converge on a dynamics experiment, because you have a double exponential gain. So don't start with the Grover algorithm, because Grover, you just have quadratic overhead. You're going to lose out immediately because the overhead on a quantum computer is going to be so large, it's going to kill any advantage you have. So you have to start with a problem that has exponential advantage, ideally some double exponential advantage, right? Then you can have hope to win, maybe, if your goal is to show supremacy, I don't know, but. So of course, and dynamics, quantum dynamics is of course something where that's the case. Random circuit, unitary circuit is nothing as similar thing. So you have this double advantage both in space and time. But it's also challenging, of course, for experiments, because if you want to measure something there, you want to do this in large systems. You want to have controlled couplings, homogeneous. You want to go to long evolution times. It's also not so easy from the experimental side of view. I want to come back to quantum transport. And go back to the situation, where we can set up a non-equilibrium initial state. For example, this charge density wave 1, 0, 1, 0, 1, 0, 1, 0. And then we let it evolve, right? And we have this unitary time evolution. And then we're going to get the outcomes of the different probability distributions of configurations. So maybe this one, but then in another shot, it could be just another configuration, 3, 4. We do this many, many times. And again, when you have these snapshots that you get, you can do interesting things. You can, for example, look at subsystems or densities between sites or subsystems here, and just count the number of particles in these subsystems. How many number of particles do we have in this subsystem as a function of evolution time? Okay. And when I plot that, that's called the full counting statistics. Okay, because we're not just knowing the mean, what is the average number of particles, we're knowing everything. We're knowing the variance, the skewness, the kurtosis, if I measure this full distribution function. And the question is, of course, can we use this to characterize quantum transport in better ways? Can we learn something about quantum transport in better ways having access to this full counting statistics? So let me show you a first experiment on this. And of course, in this dynamics, I don't know how you feel, but in this dynamics experiment, sometimes you have the feeling each one, okay, is different. In each one, we can calculate with DMRG e to the minus IHT, and then we'll get the outcome, but we're not uncovering any universal principles. So somehow it would be nicer if we would be able to uncover some universal principles in this quantum transport and not just have to calculate for each time, each system, the time evolution. So I want to maybe show you one step in this direction for chaotic quantum systems. And the idea is the following. And imagine you set up your initial it, which is, let's say, a non-eigenstate of your system. You let that evolve over a certain amount of time, and the density actually will relax very quickly to some average density. So you're going to end up with a system that does not have any density gradients anymore. So, from looking at the average density, it looks like thermalized from that quantity. However, there's actually still a lot going on. We know thermalization has to involve slow hydrodynamic modes, and these slow hydrodynamic modes emerge from still entanglement spreading in the system. So there's still a lot of entanglement spreading in the system going on. And this entanglement spreading is actually responsible for building up the right full counting statistics, which corresponds to a thermal ensemble in that subsystem. Okay. So entanglement propagation is crucial for creating the right fluctuations in the subsystem that would make that system look thermal. So how can we capture that? So actually, so maybe I should just put it in perspective. So with ETH, we know that for very long times, the system will look like thermal ensemble. We know that from the ETH hypothesis. However, ETH tells us nothing how this system evolves into this direction or the dynamical evolution. And the question is, can we find some general equation that can describe this? Now, in classical statistical mechanics, there's been this very nice new theory around like a decade now called macroscopic fluctuation theory, which allows you to deal with not only the growth, allows you to formulate a hydrodynamic not only for average quantities in the system, but also for the fluctuations in these systems. And the question is whether we could apply this also to quantum systems with the following idea. So this is the one way of writing down MFT is you have some conservation law here. Then you just have, Fick diffusion law. But then it's modified by a noise term, which is a stochastic noise term. This Ci is just a white noise term that acts onto the system, just produces very high frequency fluctuations in the system. We have to put the prefactors right to connect it to the correct fluctuations in the system to get the correct thermal fluctuations in the system. So this is the equilibrium diffusion constant, and this is the susceptibility of the system. So it's kind of like a fluctuation dissipation theorem, but for now non-equilibrium dynamics, not only for systems in equilibrium. So it's making a much stronger statement in its predictability, right? And the question is, does this work here also? I mean, here, why could it work? Well, we could maybe think that this entanglement spreading is maybe like modeling the system. This entanglement growth is like having the system connected to outer reservoirs, and just the fluctuations that we introduce from this outer reservoir into our subsystem will drive it eventually into a thermal state. Now, if this description is correct, it will have to give us, by knowing the diffusion constant, the equilibrium diffusion constant, and the susceptibility, we should be able to predict the rate at which the system thermalizes, which these fluctuations grow to their steady state value, if that has any predictability in it. Okay, so what we're really asking, is there a hydrodynamics of fluctuations? Is there an emergent hydrodynamic formulation, not only for the mean quantities, but for fluctuation? Mean is also included in this equation. If you would have density gradients, this would also generate currents, but we want to have actually a situation where the density becomes flat, so there are no density gradients. It's only about the fluctuation, okay? All right, so here's now the two cases I'm going to study with you. So we're going to do hardcore bosons. We know how to do that by now. We're going to set up this, so they are hardcore bosons are like XY model. In terms of a spin model, we're going to do it either in the case of a 1D chains of free fermions. We know that's a integrable model where we can, the U over T going to infinity makes the system behave like free fermions. And then we can couple these two 1D systems together. And then we'll have a chaotic quantum system because we now have an interacting XY model. Yes. Yes. This is for the mean. Remember, this n here in MFT is a stochastic variable. So it's a fluctuating variable. So it allows us to calculate average quantities, but also fluctuations of that quantity in a certain region. So it basically tries to say, can we capture quantum dynamics with this stochastic partial differential equation. Mind you, this is also not easy to solve because it's a nonlinear partial differential equation, because you see here that this is n-dependent, so it's not easy, but it might be much easier than solving e to the minus IHT and what you're capable of doing, right? So that's the spirit. That's the question we're asking. Does that work? Okay, and these are the two cases we have, and what we set up are systems of about 50 lattice sites in one direction. We can couple the two ladders, so it's 2 times 50, so 100 site system, and then we have many of these ladder systems, copies of those, about 20 copies of those systems that we can study. And then we can just do the experiment. We can start out with the charge density wave and then let the system evolve, and we see all these fluctuations showing up. We reconstruct where the atoms are in the lattice, and we can remeasure the full counting statistic for different subsystems and different evolution times. This is evolution time 18t. This would be subsystem size 4, subsystem size 10, and measuring the full counting statistics in that subsystem. Okay. Now, if we look at local quantities like the imbalance or the average density on each site, we see that that actually very quickly relaxes, and that's also what we expect to happen in the system. However, if we look at the fluctuations now, and have to be slow on this graph so you understand it. So here's the different cases, the 1D case, the coupled ladder case. Here's the time evolution in the system. No. Let me give you, let's say the probability of having a boson per site is 1/2. We're at half filling. Let's say we do that case. What's the probability of what's the maximum fluctuation I can have in that in the system? Well, it's just like throwing the coin n times with 1/2, right? That's the maximum. So it's just n times p times q. So we just n times 1/4. Okay, that would be the steady state, the maximum possible value I can have if I can really fully explore to the saturation value. Mind you, when we come to, for example, localized systems, this would not happen, because for a localized system, you can't spread the correlations over the entire system size, subsystem size. You will be bound by the localization length of your many-body system, which is actually an interesting way of detecting many-body localization, and we can talk about it in the end. Okay, but what you see here is like, okay, fluctuations start out 0, they grow, and then they come to their saturation value, which is just the one value we mark here. We can mark the point where they reach 80% of the saturation value. And when we can plot these 3 curves on this log-log plot, saturation time versus length of the system, you see for the free fermion case, we have ballistic spreading in the system, ballistic growth of the fluctuations, because we have a free fermion model. For the latter case, we have dynamical exponent of 2, which means we have diffusive spreading, diffusive growth of the fluctuations, which you can see here. In between, I'll come to the case in between when we have half-coupled ladders. And we can also now compare this to the variance in the subsystem sizes to what MFT predicts, where D is again the equilibrium diffusion constant. I'll come to this comparison in a second. So what you see actually, if you look at these quantities for the integrable system and the chaotic system, you see that subsystems take longer and longer and longer to thermalize, to get to the right steady state fluctuations, whereas the local quantities, they take shorter and shorter and shorter to relax when you go from integrable to chaotic. I want to show you another picture. How you can nicely understand what's going on is looking at density-density correlations. In the end, number fluctuations are nothing than a sum of density-density correlations, right? If I sum up N1 plus N2 plus N3, the densities on those sites, that would be the density of my L equals 4 system, right? And I square that, you see that it has just a sum over all the 2-point correlators in the system. So if you know the 2-point correlator, you also understand how this spreading is happening. And you can nicely see, so this is now doing, after the quench dynamics, looking at the 2-point correlator. In the free fermion case, you can beautifully see the ballistic spreading of the correlations. This is the famous Lieb-Robinson cone, right, with the linear spreading of correlations, and just would give us the correlation, the velocity of those correlations that we spread. And in the chaotic case, when we have these coupled ladders, you see very nicely how this is not linear, how this becomes a square root of t. Now you're in the chaotic case, you have diffusive spreading of correlations, And you can measure, just by measuring the envelope of this cone, you can measure the diffusion constant, right? And we can compare it to the MFT prediction, which tells us how fast this should grow, also knowing the equilibrium diffusion constant. If you couple halfway in between, you see it's interesting. It seems like you first get some linear spreading and which bends over then into some diffusive case, which is now explains why what we're seeing here in terms of the dynamical exponent is something between 1 and 2. You know, even for epsilon coupling, arbitrary small coupling, the ladder system with small coupling should also be diffusive. It just means, you know, you have to look for longer and longer times to see that diffusive spreading. How does the system even know that it's 2D? You have to give it time to explore this other dimension, right? All right, now we do this final comparison. So in the experiment, we get now the diffusion constant. We measure it to be 0.08 with an error of 5, and really some very recent calculations from Kurt von Kaiserlink and Frank Pollmann. They looked at this, and Fabian Heidrich-Meissner also. They calculated this equilibrium, high temperature diffusion constant, and you see that they agree rather favorably, I think, for a first try. So that actually works out quite nicely. And I think what's also interesting that it means that we can, if this works, this mapping holds, we can measure equilibrium diffusion constants, which are very hard to calculate for chaotic quantum systems, via strongly out of equilibrium dynamics, which gives us a strong signal in the experiment. So we can really measure something useful. Okay, as for a physicist. Okay, all right. All right, so yeah, so this is you know, what I want to tell about this fluctuating hydrodynamics. This fluctuation full counting statistics is really a powerful new way of looking at quantum transport. It's hard to calculate also so you can try it. It's really hard doing this ladder calculation with DMRG. You can't do for the system sizes I've shown you here. This is already beyond, well, try yourself, prove me wrong, and then I'm going to be happy too. But that's out of the reach for standard DMRG techniques. What's of course also interesting, you know, maybe for the variance this works, but does this MFT also fail? Could we look at higher order accumulants, which does not show this? Do we have observables, you know, where we have interference structure that would not fall into this way of describing them? Or could we make MFT more quantum? And this is not just, you know, myself dreaming. There are really people from that community. And here's a prominent person, Denis Bernard from École Normale Supérieure in Paris, who's really thinking about quantizing this, taking this description. I think it's very nice because it really tries to, you know, bring a universal effective approach to describing quantum dynamics of certain observables in a unified way. And I think that's really gaining insight, new insight, what's happening in these systems. All right, final topic before I close with MBL, just a few comments on MBL. I want to talk about KPZ. It's another it fits very well what I told you before, but it's an even more interesting case of knowing the full counting statistics, because it's going to be even more exotic than in the case of the chaotic quantum dynamics. This was a very nice work together with Norman Yao's group, and Bingtian is also here. Bingtian, where are you? Not here. There, Bingtian. So he was heavily involved in that, and Sarang. And so Bingtian's going to help me out if I need support on the numerics side. And there's actually, I should mention, a very nice new experiment from Google that I'd like to talk about also on this KPZ dynamics. So it's good, as long as we can always do the experiments first and then Google does it afterwards, I'm happy and it's okay. All right. KPZ, that is a super, I didn't know anything about KPZ. This is a super interesting topic from statistical physics. I guess, Leo, you must know it very well. I mean, it's really a beautiful topic, and it describes basically the growth of interfaces, and it's really abundant all around us in the classical world. You know, you look at bacteria growth, tumor growth, or this liquid crystals, are actually beautiful experiments by Takeuchi in this group in Japan, traffic flow, fluff fires. I didn't know what a fluff fire was, but let me show you what a fluff fire is. You have fluff on the lawn, and then it burns like crazy, apparently. I didn't know that, but you can set it on fire. The lawn is fine, so it's not burning the lawns. And children love that, apparently. So there are tons of videos on YouTube where children make a fluff fire. Yeah. And the fire front actually is also a KPZ, follows this KPZ surface. Coffee stains, when you lift off your coffee mug, it's like a KPZ stain. Ice crystal. So it's really around there. And what we mean by KPZ universality is certain correlation properties of these height surfaces. Let me contrast that compared to just random deposition on surfaces. So let's think of a Tetris kind of game where we have a surface and we're dropping blocks from above, randomly. There's somebody just dropping blocks randomly from above, and these blocks don't stick to each other. They really just fall into the line like Tetris where they are dropped onto, okay? And that would just give you just random deposition. You would just get your standard surface growth rate in the system. And now let's modify the game a bit with some nonlinearity where this block can now stick to this other block when it passes it. Okay, so if it passes one block, it just sticks to that one. And if you do that, you see this is how the surface looks like, and you can already see that it's a totally different beast. Here's some animation I found that shows you that this is how the surface growth looks like under KPZ. And something obviously completely different than this thing. So you can see it by eye. It's already clear that this is different. So how do we capture that? Well, we of course have to phrase this mathematically. So we have the height field at some point x on the surface at some time t. And this height field will have fluctuations in the vertical direction, but it also has transverse correlations across it. And that's what characterizes this. So the fluctuations, actually interestingly, there will be an average rate of growth of this surface. That's not so interesting. That's just the average rate at which we drop particles. But what's interesting, what are the fluctuations in each column? And interestingly, they don't follow Gaussian statistics, where we would expect t to the 1/4 and a Gaussian random variable distribution here. But in KPZ universality, they go like t to the 1/3. And this distribution function is not a Gaussian, but what people Tracy-Widom distribution function. It's actually an asymmetric distribution function that you can see here. Okay, so it's rather something. So you draw a random variable from this distribution function. This is this random fluctuation that you get. And so this, and also space and time correlations are slightly different. So spatial correlations with time are not connected with this dynamical exponent z, and z is not, wouldn't be 2 like in the diffusive case, but would be 3/2 here is giving a super diffusion, and beta 1/3 for these fluctuations that we see in the system. All right, and that's what defines this KPZ universality class. These exponents, correlation exponents, okay? And that's a little bit different from the KPZ equation. Where do I have the KPZ equation actually? Should show it to you. It's coming. Sorry, it's coming in the wrong place. Okay, so that's the KPZ equation generates a height field that falls into the KPZ universality class, but even proving that was actually, it took some time to show that. So this should, of course, give credit to the people who invented that in physics. There's Mehmet Kada, Giorgio Parisi, and Yiping Zhang, and who invented this equation for height field growth. And in mathematics, actually, Martin Heira got the Fields Medal for solving this equation. So what is it? It tells us about the growth rate of this height field. Here, this is the stochastic variable, the random variable. It's like the random dropping blocks from the top. This is just a spreading of the particles on a surface. When they hit a surface, they can spread out maybe a little bit. That's all standard, but what's not standard is this gradient h squared term, which is the nonlinearity, which is the sticking, which generates the sticking I talked about in this model. Okay, and this is what makes this extremely hard to solve. So it's a nonlinear stochastic partial differential equation. Remember what I told you for the chaotic dynamics, MFT is also a stochastic partial differential equation. So actually the spirit is actually very similar of trying to capture what we're going to see, quantum transport via these stochastic partial differential equations. I'm going to come why this is even relevant. I didn't tell you yet. I'm just telling you maybe an interesting story on classical statistical physics. So turns out that the physics where this was found now in quantum systems is actually in Heisenberg quantum magnets and not at low temperatures, which is maybe why it was missed. People know there we have Tomonaga-Luttinger liquids, but it's really a high temperature, an infinite temperature phenomena. It occurs for the Heisenberg magnet at infinite temperatures, and people, of course, hadn't been looking there. There's a very nice work from Joel Moore where he actually shows nicely this crossover from this TLL behavior to the KPZ behavior, just that you know where we are. So how do you measure, how can you measure that? Well, imagine you have an infinite temperature environment, and you place one spin up here, and you ask, how does this spin spread as a function of time? And how do we capture that? Well, we can capture that through this dynamical spin-spin correlation function. So this tells us how the spin at position 0 time 0 is correlated with the spin at position x time t. So what's the probability of finding the spin at a later time at that position? And if you wouldn't have known anything about the problem, if you start with this localized particle, I guess what you would have said, what I would have said, well, it's just going to be some Gaussian spreading, diffusion probably, what's going to happen. So this is going to be a Gaussian, and space and time are linked by this dynamical exponent of 2, giving us this diffusive behavior of the spreading of the wave packet. Turns out, I wouldn't be here now telling this story. That would be the answer. That's not true. What was actually found by Tomasz Posen's group in Ljubljana, a numerics experiment, when he did that for the first time, is that he did exactly that experiment, just looked at the spreading of a single particle, and you look at the distribution function, and what he actually found, what is not a Gaussian, the green curve, but it actually follows a KPZ scaling function, so a certain function that comes from this KPZ physics. And that's why, for the first time, people thought there has to be this connection to KPZ here. This plot is just a single spin. Where is it? This one. It's just a dynamical spin-spin correlation function. You put a single spin and you let it spread. So it's an equilibrium measurement, basically. You have the infinite temperature system, one spin, letting it spread. And you're asking, what is the probability of finding that spin at some other position at a later time? And if you would have, probably your first guess would have been it's diffusion, Gaussian, but it's not diffusion. It's this KPZ scaling function with rather high accuracy. Now, an interesting way you could now do this experiment, but you can measure this dynamical spin-spin correlation function also in another way by looking at the domain wall dynamics. And this is what experiments, our experiments and Google experiments have been more doing, is that they created a domain wall where you have slightly more spin ups on the left and slightly more spin downs on the right, very sharp interface, and you look at the spreading of this domain wall. Okay, now you can show that in the limit of this domain wall visibility going to 0 height, then basically the derivative of this domain wall profile is just like this dynamical spin-spin correlation function. So you've measured the same thing, but strictly speaking, only in the limit of eta going to 0. But we're going to test it even beyond that limit. Now, here comes the conjecture now. Here comes the big leap of faith one has to do in this story. So if we say what people know from quantum numerics, I told you this is pretty established. This dynamical spin-spin correlator is the KPZ scaling function. From KPZ equation, we know that correlation of this height field can be described in the following way. So this is just the height field at xt minus the height field at 0 and subtracting this boring average growth rate in the system. That's then the second derivative of this correlation function of the height field, which is just the correlator of derivative of the height field at xt with derivative of the height field at 0, 0, is also the KPZ scaling function. So then people say, well, maybe then these are the same thing. Then maybe this dynamical spin-spin correlator from quantum operators is the same thing as the correlation function of the stochastic variable, which is the height field. And then we can identify, then we can take the next steps and say, well, maybe then the spin operator is just the derivative of the height field. We can just describe the quantum operator with its fluctuations by the derivative of the stochastic variable, the height field variable, and then use kind of like KPZ to describe that. So that's what people think or thought. And then if that's true, of course, that has a lot of consequences, that has a lot of predictions, because if this is true, then a lot of the fluctuation properties of the quantum operator should be fall into this KPZ universality class because they're described by this fluctuating height field. All right, so let's test this. Let me skip this quickly. Yeah, I should mention briefly that there were actually very beautiful first experiments on measuring just this dynamical exponent by experiments by Alan Tennant at Oak Ridge on 1D systems. Should give credit to that, where they measured slightly lower than 3½ dynamical exponent, but there was maybe the first hint that something is different here at the Heisenberg point. And so what we're going to do is we're going to work exactly at the Heisenberg point. Remember that's what we get for bosons or fermions automatically in the Hubbard model. We get automatically this isotropic point. And we're going to check how the system behavior changes if we either break SU2 symmetry by magnetizing the system, or we break integrability by going from 1D to 2D, how the transport changes. All right, so this is the system. 50 spins and 20 copies of these 50 spins. So 1,000 sites. But each 1D chain is 50 side chain. Bosons, yes. But doesn't matter. It could also be done. Just needs to be Heisenberg. Doesn't matter whether it's ferro. It's at infinite temperature, so it doesn't matter whether it's ferromagnetic or anti. But here it's bosons, yes. How do we prepare this domain wall state? Well, we can just shine light on half of the system and flip half of the system in its spin. So that's how we create a very sharp domain wall in the system. We can change the visibility of the domain wall by applying random magnetic fields, kind of local light shifts that look like random local magnetic fields, which makes the spin process a little bit arbitrary in each direction. And that's how we can reduce the visibility, the contrast of this domain wall. Okay. All right, and then we do the experiment. This is the full contrast domain wall. You have here the spin ups, here the spin downs, and then you just let them go as a function of time, and then they will just propagate from left to right. And then you just count how many particles have been transferred from left to right. You again measure the full counting statistics. And again, from that, you can not only get the average, you get the fluctuations, the skewness, everything in this distribution function, right? All right, so you can do this for the full polarization, also for reduced polarization. And let's look at the average number of spins that have been transferred. So this is just the average spin number as a function of time. This is the experimental data. These are the magnetization profiles at these different evolution points. And if I fit the data with t to the 1 over z and fit, I get a z of 1.54 with an error of so very respectful. Okay. And just plotting it on a log-log plot, you can really see that it's totally different from ballistic, which is this blue curve, or diffusive, which would be this red curve. And if we do a scaling collapse with this dynamical exponent of 3/2, all these magnetization profiles nicely collapse onto each other. Okay. When we go to 2D, what we actually see when we couple the system fully into a 2D system, 1,000-site 2D system, we do the same experiment again, measure the average transport, and fit again. We see that we get diffusive transport, like what I showed you in the other chain. The system becomes diffusive. We get chaotic quantum evolution. And I'll skip the magnetizing system. So important. So we can put the dynamical coefficients onto a graph here. So 1 dimension non-magnetized gives us super diffusion. 2 dimension gives us diffusive. And the one I just skipped actually would give us ballistic propagation. So all those cases give us something different than the 3/2. So it really seems we need to be at this very special point to see the super diffusive dynamics in the system. And now it comes to a bigger step. And this is now looking, we can not only look at the average quantity, we can look at the fluctuations also. And if the system, if the height field corresponds to the quantum operator of the magnetization, then the fluctuation properties should be the same. Meaning, remember, the fluctuation properties of the height field in KPZ should scale like t to the 1/3 and Tracy-Widom, right? And if you look at that skewness, the standard deviation in the system, you indeed see that for the 1D system, this has this finite skewness in the system in reasonable agreement with what one expects for Tracy-Widom distributions, where if we go to the 2D system, we see that goes down and down, becomes more symmetrically, just like a Gaussian. If we look at the standard deviation growing over time, this should be going like t to the 1/3. And indeed, for the 1D system, these green points, we fit a beta coefficient and we get 0.31 with an error of 1. And the red one would be diffusion. So that's all really nice, because it seems to paint a picture, at least, that we see in the average transport, in the fluctuation properties, we see that there seems to be corroborating, and that it indeed is in this KPZ universality class. Now, just putting in this perspective before I jump to the conclusion and the maybe bigger question, which is unsolved so far, is this type of full counting statistics, we can not only do at the Heisenberg point, and here I just show some numerics from Sarang, Al Morningstar, Romain, and Vedika, doing this on the XXZ chain in the Ising axis case, where you have delta larger than 1 isotropy. And you can see you can also measure full counting statistic distributions there. You see, interestingly, one thing I want to point your eye to is that in the magnetization in the distribution function, the skewness actually depends on the domain wall visibility that you see in the system. So for large domain wall visibilities, you see it only drops very mildly and then goes to the steady state value. Whereas for low domain wall visibilities, it seems to drop very quickly to 0 and then takes a long time to recover to the actual steady state of the distribution function. Okay. Why that is important, I'll come to in a second. And of course, the general question is, can we use this powerful tool to discover new regimes of quantum transport in these systems? Yes.
You were saying you can get the counting statistics that you were showing.
Yes.
So like, how does this work? You have software that scans these images, or I mean,
yes.
You're not counting these by.
No, absolutely not. That would not go down well with the students, I think, if they would have to count the images by. Now we have, of course, sophisticated image analysis software that takes an image and tries to identify. In the end, it just spits out a matrix, 1, 0, 1, 0 matrix, where which sites are occupied and which sites are empty. And then I could pass this on to you, and you could immediately use that data and calculate everything from that. Interestingly, we're now getting in touch with astronomers because they have very similar problems when they look at these, how do you call this, Kugelhaufen, these dense star clusters. You know what I mean? When you have these star clusters and you want to deconvolute them, this is like our atoms, a similar problem to finding our position of atoms on the lattice. So we're now starting to talk to them to find some more sophisticated algorithms for doing that. Yes.
How do you prepare the initial domain wall state and
yeah. So everything is spin up. That was just the mod insulator state. Okay. Then on half of the system, we shine a laser beam, which does a spin rotation, a sigma x spin rotation on half of the system. So that, and we can do that really sharp. You can see the domain wall sharpness is really just one lattice side. Perfect. Yes. For larger, yeah, we can't do that, but the calculations have been done, and it seems that also it falls into KPZ universality class. Yeah, you are in principle, yes. We're so happy that this works already with 2 spin components. You want to do it now with the, I don't know, strontium spin 5, 6 system or something. In principle, yes. In practice, we're very happy to do this with 2 spin components. So why am I saying, so let me just summarize here. So we indeed see this dynamical exponent 3/2 superdiffusion. We see the right fluctuations. We see also for this large domain wall height skewness of polarization fluctuations comparable with this Tracy-Widom distribution. And we see if we break SU2 symmetry or integrability, we destroy this KPZ behavior in the system. Now, the story is not settled. What are the big open questions? One big open question is, if what people conjecture now is that, knowing from classical models more, is that the superdiffusive transport is really only a transient phenomena for finite domain wall heights. Only in the limit of domain wall going to 0, you have this really perfect KPZ regime. So you would think that maybe this dynamical exponent as a function of evolution time goes down. And there are indications here, Bingtian's calculation on that actually, where you see if you go to long evolution times and you fit the dynamical exponent, you can see this is starting to bend a little bit down there. Yeah, and the question is, does that cross over into diffusion in the end? Open question. Another open question is the skewness. What the Google team actually was looking at now, they were looking especially at the low domain wall visibility case, and they indeed see a very rapid drop of the skewness of the distribution function, and it's just staying 0 for them. But in their case, they can only do rather medium or short time evolutions up to 20 tau or to 25 tau. What I showed you was up to 50 evolution times. So what could be happening here, they're just not waiting long enough for this thing to recover to the steady state skewness that I showed you before, that we know what happens in the XXE model. What could also be, it could also be that, the system crosses over into diffusion before this skewness recovers actually its proper value. That would mean it's not KPZ on that time scale. So that's an open question. We don't know right now. We need better numerics or better experiments, and both are extremely challenging. So if one of you wants to try that and do that, please do, because both is extremely hard, because you need long time evolutions, really long time evolutions, and large system sizes. And maybe in the end, if that's not true, then maybe we are seeing a new universality class. Maybe that's not KPZ, but something different, which just in some observables smells like KPZ. We don't know. What would, of course, also be wonderful, and I again would like to motivate if anyone wants to work on you on that, can we derive this stochastic partial differential equation? We don't know it. I'm always talking about KPZ, but we don't know what this stochastic PDE is that describes this magnetization transport. We only know that it's in this, seems to be in this universality class. So can we somehow derive this a better way than these empirical ways I showed you for deriving why these stochastic PDEs should describe quantum transport? Okay, but that's exciting for doing research, right? Yes. Yes, but the question is, can you capture this growth? That was what I tried to explain in the first case, in the chaotic quantum. Can you describe the growth of fluctuations or higher order moments? Skewness would be a 3-point correlator, that is then, or kurtosis would be a 4-point correlator. How do these, what's the dynamical evolution of these variables? That's the question. And can you capture them via these stochastic PDEs? That would be nice, because it would really give us a universal way of describing quantum transport. I mean, it really would bring us away from, okay, we always have to do the next DMRG calculation, the next DMRG calculation to understand what's going on, but we really have a new fundamental principle to describe that. That's why I think it's interesting. I don't know if it's the right way. It's just conjectured. I'm giving you some hints why the experimental data supports very much that there could be such a description. Yep, please. Yes, in principle, the infinite temperature would only be realized for this completely dephased, basically completely random spins, which we can only approach when we take this domain wall height to 0, basically. And we would also like to have, of course, a theory that can describe any finite domain wall height transport. So Sarang is trying this, and I hope others too, and that would be very nice. So yeah, I think it's a really nice example of theory interacting with experiment, with different experimental platforms, neutral atoms, superconducting systems. Try yourself on this problem. It's a really interesting physics problem. Okay, I think I don't have time anymore for MBL. Just one quick comment on MBL, because you've been hearing about it. And one cautious comment I want to make is that MBL, really is about very long time evolutions. You have to go to very long time evolutions to say anything reliable in the experiment. Just to show you, for example, when we did this experiment in 2D, where we prepared a stripe pattern, we let it evolve in a disorder system, and we look at the decay of the imbalance. You see kind of multiple time scales emerge in a very quick one, then one that can be several hundred tau time scale until some steady state is reached. And then, we can only put a bound on this last thing. We can, how good can we say this is a plateau? We can only say, well, the upper bound the lower bound, sorry, to any potential exponential decay of that last part is around 2,500 evolution times. So experiments are always going to be limited, but it really means you have to go to very long evolution times to say something. And that's what makes it very hard, I think, to analyze some of the questions you've been hearing about in the conference and trying to understand them. I would be wonderful if some one of you comes up with new ideas how we can address this, but please also think of a protocol, experimental protocol, what you want us to measure. That's the first question I will ask you. All right. Just finish off maybe, where next. I hope gave you an overview of what, some of the things that have been done with cold atoms. There's like super interesting stuff and going on and combining the world of tweezers and optical lattices. There's Wasim Bakar's work in Princeton on optical tweezers, creating flexible Hubbard arrays. There's the work here from Adam Kaufman in combining the tweezers with lattices. And there's also really nice work from Monica Schleyer-Smith at Stanford, and who's there at Berkeley? There was some, Dan Stamper-Kern, sorry, on putting atoms in cavities and having long-range interactions between them, programmable long-range interactions. I just flash up our own efforts. You know, this is where we're going right now. This is a lattice with about 30,000 sites. So where you can see individual atoms. They're not yet sorted or ordered as nicely, but you see where we're trying to go. We're combining this with tweezer arrays. So we want to have this tweezer array being able to deterministically place atoms on this grid of lattice, which you can see here, to harness the benefits, you know, of both. And I think that's going to be an exciting direction. And Adam here in Boulder has especially shown in his first experiments that this is really promising. Okay, I have to give credit to the people. Just let me finish. Who've been doing the work on the cesium experiment. This is jointly led with Monika Eidelsburger together, and actually the work on the latest work that you've been seeing, that was from Julian Wienand, Simon Karch, and Alex Impertro, and in joint theory with you and Romain and Sarang. And then there's the lithium team I talked about on spin charge separation. That was the PhD of Jaya Vijayan, and the new low temperatures achieved in the lab in postdoc team from Thomas. And here's the rubidium team. You know Suchita, she's here with you here. And she's being our new graduate student on the experiment, and KPZ experiment has been done by David Way. All right, I think I'm on time. That's it. Thank you very much. Yes. In the presence, well, in MBL, I don't think in the noise, typically when it couples, if the spectrum of the noise would be benign, then maybe, but that's unlikely. So from the outside world, it will not survive. So that's for sure. Our systems are always going to be coupled to the environment. And that's why we are always going to thermalize in the end. But I don't know, Leo disagrees with me, but I think I see the situation very similar to like what one has in a quantum phase transition. If you think about a quantum phase transition, in quantum phase transition, you have something critical coupling parameter, you have temperature, you have some critical point here, but no experiment ever works at t equals 0, right? I mean, so we are always going to be working at some fine. What does that mean? That means that, you know, any divergences you have in that region will always be cut off at some point, will be not going as large as you want. And I think that you could make the same plot here. There will be some rate, some coupling rate to the outside world, let's say some gamma that we have here, and some tuning knob as well. And that just means for us, we can only observe these phenomena for a finite amount of time. I know, but okay. That's fine for me. It doesn't mean that MBL is a useless concept. I think that's totally going too far. I think it's still, and as we've seen in the new IBM experiments, you know, the idea of Lioms, I mean, it is useful to think about these systems in this way. Maybe we're not capturing all the subtle resonances in the system, but we're maybe already capturing, you know, 98% of the physics in these systems. So I think that's useful, right? It's not completely useless. And I don't know, I think of it more in practical terms. I think, unfortunately, the discussion has gone into a more academic discussion, but yes. But I would hope really, that's why I think I would really hope we can settle this, bring this from the academic realm back to a testable experiment. So that's why I would really love to see somebody proposing an experiment where we can do this, not on astronomical timescales, tell the difference. Yes.
You mentioned that when trying to image the atoms that are too close, you have issues resolve them.
Yes.
Is it possible to like adiabatically expand it?
Yeah. Very good. This is, yes, you can do that. Markus Greiner is doing that in his new erbium experiment. We call that an accordion lattice for obvious reasons. So you have your lattice first like that, which is closed space. You make counter-propagating beams, but then you, let's say, dynamically change the angle between the two interfering beams. That means the delta K vector gets smaller and smaller. And that means the spacing gets larger and larger. And then you can indeed pull them apart, and then you can image them much easier because you just need, now they are at large separation, you just need a few photons to detect where they are. Absolutely. Yep. Steve.
So it's really beautiful, but I think I'm still confused
Okay.
a little bit about the mapping to the KPC story with your domain wall. So like with the Tetris problem, right? There's two space dimensions and time, but then you kind of describe what's going on with a function of one dimension, height function, position in time. In your one-dimensional chain, where you have a domain wall, like it feels like we're short one dimension. I can't quite visualize.
But we also have S of x of t, no? Like
Yeah.
the height field is also h of x of t.
Yeah. I'm still a little lost.
Let's talk about it over coffee, yeah. Yes. Easy access regime. I have to look it up. I can look the numbers up. We didn't, Wolfgang Ketteler has done some nice experiments in this direction. So I can, it depends on the scatter, you know, the Feshbach resonances to tune that. I can look it up and tell you how far we can go. I mean, we can go completely XY. This is the hardcore boson model. This is just XY model.
I
Right.
guess I was just wondering if you go to a point where you start seeing sort of effective domain wall concepts.
Absolutely, super interesting question. I think doing that with tunable XXZ models, exactly what I showed you here, it would be really nice. Absolutely. Last question, maybe. Yeah. Well, this is what Tomasz has been looking at. There are these Landau-Lifshitz classical spin models, and from those he finds that this KPZ is transient. That's why he conjectures it's only a transient phenomena. I would say sorry, Tomasz Posen. So I can send you I can send you the paper on that. I would say we still need to, the quantum could be different. So right now from the numerics, we don't have any evidence for that. The timescales seem to be different. Could be just a prefactor and maybe the thing happens just 10 times longer it happens, but we don't know. This is why, you know, it's really a great problem. If you really have a great numerical method that can do quantum dynamics, this is a problem to try yourself on. You can solve something. Okay. All right. Well, thanks a lot. Been a great crowd. Thank you.